So we started recording for today's class. I would like on our last class we discussed a problem of a bit of a problem for these questions, and we solved what happened here. I would like to show a bit more detailed version for this question to make some additional sense with you. I'll take this thing out. So let's take this question out. Okay. So already we have 4 individual intensities labeled over here. So the couple of things that we have to understand that when the incoming intensity comes in, it undergoes a decrease of its intensity, attenuation to the thickness of the material. It undergoes another decrease, and that the muscle fat boundary, whenever it gets reflected, a certain portion gets go through, and then the other part goes by. So this I4 is basically a three different reduction in reduction three different not different, I mean reduced 3 times reduced intensity for the incoming intensity. These three reductions can be given by, let's say if I get I4 in terms of I1, the first thing that you get is e to the power minus mu x, that's for the going thickness. Then you get another reduction, that is z1 minus z2 whole square divided by z1 plus z2 whole square. This is the reflection reduction. And then you have the reduction, thickness reduction once again, e to the power minus mu x. So that's what happens for the incoming intensity. This is a pretty simple example. I don't expect more complicated examples to show up, but just in case if more complicated examples do show up in your examples, then what you're going to do, let's say if we consider 3-layer boundary, something like this, consider this part. So let's say this is it. I'm going to color them for easy understanding. So let's say make this light yellow representing fat, and maybe label this red representing muscle. Too red? No, it's all right. So what I'm trying to show you over here, that if we have 2 different boundary, so in this case, let's say beyond this fat muscle boundary, we have bones. So let's say we have another rectangle over here. This should be bones. I can label the bones using maybe ash color, representing bones. So I'll write simple words over here just to make sense. This is our fat tissues. This is our muscle tissues. This is our bone tissues. So let's say we're going to send in the entering intensity is, let's say I1. As it comes in over here, let's say it hits over here at an intensity of I2. As it enters over here, let's say I'm naming this intensity as I3. As it traverses through this medium and reaches up to this boundary, let's say this intensity is I4. So take a good look. What is happening when this intensity, or when this ultrasound pulse or X-ray wave will eventually reach up to this part? It will undergo another set of reflection. So the same sequence will happen again. Only in this case you'll have a lot more variables to deal with. So just to make easier sense, let me just write a couple of things. Let's say over here, e to the power minus mu x, this is a factor. Let's say I'm gonna name this as a reduction factor 1, just not to write this every single time. And over here, the e to the power minus mu x, let's say I'm gonna write this as reduction factor 2. I'm just using these terms. These are not your syllabus terms. I'm just using these terms so that I have to write less, or maybe I should not, so that more variables make it more complicated, to be honest. Disregard that. Let's say e to the power minus mu into fat, and this would be e to the power minus mu into muscle. And for the reflection boundary, for the muscle, for the fat muscle boundary, let's say for this boundary, the reflection versus intensity is given by z1 minus z2 whole square divided by z1 plus z2 whole square. This is the fraction that we use. Let's say this part is reduction factor, reflection factor for fat muscle. And over here in this boundary, we're going to have a similar reduction factor. Let's name that reflected by incident is given by reflection factor for muscle and bone. So I'm labeling all these factors just because I wanted to bring in a second layer in this whole discussion and talk to you about these individual parts for what happens to if we have two different layers to work with. So just to make sense, let me name the other parts. So I'm going to use blue over here for the reflection parts. Let's say I5 reflects over here, I6 falls over here, then I7 comes in here, and I8 is the final wave which we are going to get. So what I want to do right now, I want to express all of these I2, I3, I4, I7, I5, 6, 7, 8 in terms of I1. So if I want to go ahead and do that, how can I do that? Take a good look and try to understand and counter my argument if I'm wrong. If you think I'm wrong, you please correct me. So I1 is the incoming intensity. So I'm starting writing with I2. I2 would be given by I1 into e to the power minus mu of the fat boundary. That's it. I3 would be the I2 multiplied by the reduction factor. Now, there is a problem. This would not be I3. I'll tell you why. I3 is the part that actually goes into the muscle boundary. What you get in this equation, have a look over here. This numerator over here actually gives you the reflected part. So whatever that got reflected off this boundary, whenever this boundary change happened, that is the that is the IR. I3 is the transmitted part. So I3 would not be I2 into RFM. This will not be true because that is supposed to be the reflected part. So this is wrong. So what would be the I3? I3 is the transmitted part that actually goes through the boundary. This would be
1 minus
given by
RFM.
I2 minus I2 into RFM. Try to understand this thing. This is the I3 is the transmitted part. So I2 is the incident part on this boundary. From this part, I2 into RFM, this is the reflection fraction. This part of this is the amount that is going to be reflected back, which I did not label over here because I don't want to work with that. The part that is transmitted through would be the remaining amount because energy is conserved. So the incident intensity is equals to transmitted intensity plus reflected intensity. So that's why this minus sign comes in. এই equationটা বুঝছো কিনা দেখো বলাপান. It's important that you understand this equation part. This is the new part for my discussion. Does this part make sense?
স্যার আরএফএম এর ব্যাপারটা বুঝলাম না, এই জিনিসটা
RFM
আসলে
is
কি?
the short form of this whole fraction. I did not want to write the whole of this fraction everywhere. That's why I just named this thing as the reflection coefficient between the fat muscle boundary. I just named
ও
it
আচ্ছা,
for my convenience. This is not a variable that is named in your syllabus. I just do not want to write this bulky thing everywhere. That's because I want to keep the equations
স্যার I2 RFM মানে হচ্ছে the part of I2 that got reflected from the boundary of the medium.
precisely.
আচ্ছা, ঠিক আছে।
So if you subtract it from the incident amount, you get the transmitted amount. এই কোশ্চেনটা সবার বুঝা গেছে কি? Are we clear with this one?
Yes, sir.
Yes, sir.
So then if you start from the I3 to I4, then you can work it around by the same one. Have a look. Now I can write I4 in terms of, now we know how much is I3. So I3 is incoming. So you already have the value of I3. So the next thing you have to define is I4. I4 would be I3 multiplied by e to the power minus mu into the muscle boundary thickness, whatever the muscle boundary is. Then comes, this is the intensity that falls over here. Now have a look over here. For this figure, I did not label how much part is actually transmitting into the bone. The next labeling that I have, which is I5, is what is the part that got reflected. So if I want to go ahead and write the I5, this has to be the reflected fraction of the I4, which means in this case, I will only write I4 multiplied by R of muscle and bone boundary. That reflection factor would be the thing, because I5 in this case is the reflected fraction, not the transmitted fraction. For the transmitted fraction, we have to go for the subtraction, but for the reflected fraction, the simple multiplication gives you the value. এই পার্টটা কি বুঝা গেছে?
জি স্যার।
And then this will travel from this boundary all the way to this.
স্যার রিফ্লেকশন কনস্ট্যান্ট তো দিয়ে দিবে, রাইট?
Well, it can vary. যেমন হচ্ছে এই কোশ্চেনটাতে যেটা করছে সেটা রিফ্লেকশন কনস্ট্যান্ট গুলো দেয় নাই, আমাদেরকে অন্য ভ্যারিয়েবল গুলো দিয়ে দিচ্ছে, আমাদেরকে রিফ্লেকশন কোএফিশিয়েন্টটা বের করতে বলছে। ওই যে এটা C3 নাম্বার কোশ্চেনে যে পার্টটা ছিল, যে ক্যালকুলেট দ্য ভ্যালু অফ I2 by I3. I2 by I3, sorry, I3 by I2. I3 by I2 is basically the reflection coefficient. So if they did not give you the specific acoustic impedance of both the medium, you might have to calculate that from this thing. Irrespective, one thing you should always take understanding that if you understand the conceptual, you should be able to do the math. The relevant or required data would always be provided to you. If they are not provided to you, then you have to understand that there you have to bypass that method and approach the problem in a different angle. So that's my point. But necessary data will always be provided to be able to do the calculation. So if I now try to define I6 would be the thickness reduced part for the muscle. That's pretty simple. This would be I5 multiplied by e to the power minus mu into mu multiplied by the muscle boundary, muscle thickness. And then I7 is entering into the fat tissue. So I7 if you compare between I7 and I6, I7 is the transmitted part, not the reflected part. So I can write I7 equals to I6 minus I6 multiplied by the reduction factor of this boundary. Thank you. So this is R into FM, fat muscle boundary reduction factor. So that's the transmitted part. And then finally, the I8 is very simple. I8 equals given by I7 multiplied by e to the power minus mu into f. So that's your final expression for the I8. There are a lot of variables involved over here. I highly don't expect that this would be given to you in the example. But the only reason, someone sent me a message, I'll respond to this in a bit. আচ্ছা হ্যাঁ মুগ্ধ, ঠিক আছে, সমস্যা নেই, প্রবলেম দিতে থাকো, আমি আলাপ করবো। The only reason I wanted to show you this two-layer boundary is to introduce you these subtraction factor, that whenever you are trying to find out the transmitted proportion, you cannot directly do it by multiplication. You have to separate it from the incident amount, the reflected amount, and then you can get the transmitted amount. এই পার্টটুকু আমি হাইলাইট করার জন্য এই ডিসকাশনটুকু করতেছি। এই কনস্ট্রাকশন ইকুয়েশনের বিল্ড আপ গুলো বুঝা গেছে কিনা আপ সো ফার, মানে the concept that is involved within, irrespective of the calculation. If you have to do some calculation regarding these values, the necessary values will be provided to you in the question paper. So don't worry about that. If you wonder এতগুলা variable calculate করা possible, হ্যাঁ possible. Given enough data, you can calculate everything. This is just a very basic simple process of মানে তোমরা ছোটবেলায় simplification করছো না, যে প্রথমে ব্র্যাকেট করতে হয়, তারপরে অর করতে হয়, তারপরে ডিভিশন করতে হয়, তারপর মাল্টিপ্লিকেশন করতে হয়। So sequentially সবগুলো করতে হয়. This is something like that. This is sequential math. You cannot directly jump from I2 to I8 directly unless you have a super brain. You might be able to do that. I cannot. So you have to do this sequentially. But if you know how to do this, you can do this. So that's the whole point of this discussion. Any questions so far? Anyone? No. All right. So we'll skip this discussion and get into something else. So Shubhra gave us some problem for the electromagnetism worksheet. So we'll pick that up. I prefer not to, for everyone, I prefer not to discuss problems that we have already discussed in our solution classes, because you can actually find out those solutions over here. But just in case if there are problems that I personally feel that which are pretty likely for you to forget them, I'll definitely help you, no big deal. Because there are certain questions which even after repeated discussion tends to slip out through your brain. They don't tend to get traction. There are certain problems like that. I totally agree with that fact.
স্যার 1b3 তে বেসিক্যালি এক্সপ্লেনেশনটা আমি বুঝতে পারিনি।
Oh, sure, I'll help. Question was the statement explain how the capacitor may be used to smooth the output from the rectifier. You may draw on figure 6.4 if you wish. So you may, in this case, has to be interpreted as you should. The capacitor will be connected in parallel with the load. So you can connect a capacitor right around over here, or you can connect across the SQ junction over here. Electrically, they're the similar connection. How? So that's the state part. So you may draw on a diagram, basically does this part. Then the concept part of the explanation, that how does the capacitor provide smoothing? The capacitor charges up for a small duration when the voltage of the supply goes up, and as the voltage of the supply starts to drop from its maximum value. So drawing that I'm trying to talk about, let me find where is my, okay, it's not on. এটার জন্য নাম কি, full rectifications,
Bridge rectifier.
full rectifier with capacitor. I don't need a filter. Yeah, beautiful, got it. We have the graphs as well. So this is the scenario. With the full bridge rectifier, without the presence of the capacitor, the output voltage would be these purple lines. Whenever we introduce the capacitor, what the capacitor does, when the supply voltage goes up from here to here, the capacitor charges itself, and for this duration the supply also runs the load. In this case, the capacitor is charging, so capacitor is absorbing energy, not giving out energy. When the supply voltage starts to drop from its peak value, capacitor is now at a higher voltage. Capacitor cannot drain to the supply, so the capacitor will now start to feed the load. So capacitor in this case comes to the rescue, that it will not allow the voltage to drop as fast as the supply drops, so it will drain slowly because of its discharging behavior, and within this time it will discharge in this amount, and within this time period the supply voltage will drop to zero and once again rise up to this much value, and this is when the capacitor will start to charge once again. So for every part of this slightly zigzag curve, the increasing part of the parts where the capacitor is charging up, and the decreasing parts of the parts where the capacitor is discharging. So
So sir,
what
basically
the
roughly,
way it helps is that it reduces the amount of variation of voltage fed to the load. I mean, if the capacitor did not exist, the voltage across the load would vary this whole cycle value, maximum over here, zero over here. Introducing the capacitor enables us to reduce the variation. হ্যাঁ বলো।
so sir potential difference টা মেইনটেইন করছে across the load so that continuously যাতে একই ভোল্টেজটা মেইনটেইন থাকে, so like if the device is fixed to work for a certain voltage, ওইটা হচ্ছে continuously হতে থাকে যেতে,
Well, I
like
would
that,
not
right?
What you said is absolutely correct, except for a small part. I would not prefer to use the term that the capacitor and it makes sure that there's a constant voltage output, where constant is a pretty hard term. But what better to write is that capacitor provides less varied voltage to the load supply, less varied, because whenever you introduce the capacitor you still have ups and downs. You see, this is not this black line is not precisely a straight line, but this black line has less variation compared to the purple line. So capacitor reduces that grainy behavior, or reduces, I shouldn't use the term grainy here, it reduces the variation amount, or you can say that it makes the output voltage more stable.
স্যার ওরা আসলে মার্ক স্কিমে দিয়েছিল মেইনটেইন স্পিডি, এই কথাটা তো আসলে বোঝায় যে কনস্ট্যান্ট ভোল্টেজ মেইনটেইন করতেছে বা সামথিং লাইক দ্যাট,
দেখতেছি
ওই কারণে কনফিউজ হয়ে গেছিলাম।
Sure.
লাইক মেইনটেইন স্পিডি তো স্যার আসলে লেস ভ্যারিড ভোল্টেজ নাকি আসলে কনস্ট্যান্ট ভোল্টেজ?
1v3 তে capacitor connects excuse reduces to load when current in load decreases, just the maintenance PD across load or other relevant comments. Okay, they have used the maintenance PD over here. This actually is a pretty old mark scheme. I think this is Majun 12 or something like that. Sorry, Majun 02 or 03. You can see the writing over here. This was an image crop. I would appreciate that if you don't write the word term maintain. What I would recommend that you write, because they have also written the other relevant comments. So what I would recommend you write that thus capacitor maintains a less varied voltage across the load, which is expected, or it reduces the variation of voltage across the load. Or you can write that thus maintains nearly constant voltage. Do not use the term constant as a single term, because the voltage actually,
or sir maintains a less varied potential difference.
that perfectly makes sense. Yes, that's what I meant.
আচ্ছা স্যার, ওরা এখানে শুধু এসকিউর অ্যাক্রসের কথাটা কেন বলছে না, লোডের অ্যাক্রসে যে হতে পারে এই কথাটা জাস্ট মেনশনই করলো না?
SQ and load are basically the same point in the circuit. Have a look. If you connect
জি
it
স্যার, সেটা আমি
across SQ
বুঝতে
point
পারছি,
and
কিন্তু
across SQ, I mean, they prefer SQ, but you can connect it anywhere. I mean, SQ connection এখানেই physically হতে হবে না, SQ connection তুমি এখানে দিলেও physically একই হইতেছে. Even if you connect a connection like this, horizontally comes in and then vertically connects over here, that's also a parallel connection across SQ. Also works, doesn't matter.
জি স্যার।
Then we have 2D2.
স্যার এরপরে জি স্যার, ওইখানে স্যার আরএমএস ভ্যালুটা কেন 3 হবে এটা নিয়ে?
Because if you modulate this graph, whenever all the rectangular shape graphs goes on the top, you have a perfectly flat line. It's easier for me to show if I just show it by a bit of a drawing.
Sir, for RMS value, we are not considering any like negative voltages or negative currents.
RMS voltage means that if you do the bridge rectification, and then what do you get? So let's say I am taking out this part, so lower part. I could actually copy it. Acha, never mind, I have moved it, doesn't matter. And then if I flip vertical and place it over here and do the transparent selection, uh, you can see that whenever it is placed perfectly, we are losing the original lines. But get my point that whenever we'll play, acha, never mind. Whenever we'll flip this over and flip this over, if we flip this entire rectangular voltage, you're gonna get a perfectly horizontal line over here. Take now. You're not gonna get any ups and downs like a modulated sine curve. The reason we have
Yes,
to
sir.
use RMS value for the root 2 part, because whenever that zigzag graph was made into a flat line to give us the same heating effect, then this peak would somehow go down, because all the peaks over here are flat. So whenever you modulate this graph, you get a perfect flat line. That's why that's basically is your RMS value. In this
Sir,
case,
bridge rectification তো বেসিক্যালি সবকিছু মডিউলেট করে দিতেছে,
yep,
রাইট? কারণ
that's the
ওয়ান সাইড দিয়ে ফ্লো করতেছে না পুরো।
hmm.
ইয়া, ওইটাই আর কি, বুঝতে পারছি।
স্যার
হ্যাঁ, ফাইন, বলো।
স্যার কার্ভ হইলে কি হবে, মানে নিচু হয়ে যায় বুঝলাম না, মানে বললেন যে কার্ভ হইলে হচ্ছে নিচে নেমে যায়, মানে যদি মডুলাস করি।
বলতেছি, মনে করো এটা হচ্ছে তোমার কারেন্ট ভার্সেস টাইম গ্রাফ, ঠিক আছে? তুমি এখানে একটা কার্ভ আসছে, বিজেটিফিকেশন করার পর একটা কার্ভ আসছে। এইটার যে এই কার্ভের যে এনার্জি আউটপুট, এই এনার্জি আউটপুটটা তো ইউনিফর্ম না, বিকজ ইট ইজ কন্টিনিউয়াসলি আন্ডারগোয়িং চেঞ্জ। ইফ ইউ কনসিডার দিস হোল এনার্জি আউটপুট and try to get a uniform current, try to define this power output of this curve current with a constant current, DC current, the value that you're gonna get the DC current is somewhat gonna be somewhat less than the peak. That value is usually Imax by root 2. That comes from integration. So the total heating effect under this thick blue line, this DC current, is equivalent to the total heating effect of the total power supply by this curved effect. That's why it goes down. That's why the root 2 comes in. But if for a rectangular graph, that's not the problem, because if you modulate the rectangular graph, you get the whole peak as a horizontal straight line over here.
ওকে স্যার, বুঝছি।
It's about averaging the power. That's the key part. বুঝছো?
জি স্যার।
Okay.
স্যার, ডিরেক্ট কারেন্টের জন্য যেটা আসলে পিক ভ্যালু, এটা তো অল্টারনেটিং কারেন্টের আরএমএস ভ্যালু না?
Yes.
মানে ডিরেক্ট কারেন্টের যেটা পিক ভ্যালু। হ্যাঁ,
Direct current value একটাই, so you shouldn't use the term peak. Direct current value is the RMS value for the alternating current. Yes.
স্যার 4C তে যে প্রবলেম ছিল স্যার, আসলে ইকুয়েশনটার সঙ্গে রিলেট করে এক্সপ্লেইন করতে হবে।
এটা তো আমরা ডিসকাস করছিলাম।
স্যার, এটা করছিলাম।
হ্যাঁ, এটা তুমি আমাদের ওয়ার্কশিটে ডিসকাশনে গেলে এটা পাবা। এটা ওখান থেকে একটু দেখো, ভিডিও থেকে, না বুঝলে আমি পরে আবার বুঝাই দিব, ডোন্ট ওয়ারি।
না স্যার, ওটা আমার প্রবলেম ছিল, ওটা পাই নাই আমি ভিডিওতে।
The question says the Marie flux density B at density BD from a long straight wire carrying a current I is given by B equals to 2.0 10 to the minus 7 I divided by D. Use the expression to explain why under normal circumstances wires carrying alternating current are not seen to vibrate. Make reasonable estimates of the magnitudes of the quantities involved. So first of all, you have to make reasonable estimates of I and D. If you have two current carrying wires, one live, one another neutral, placed side by side within a cable, then what is the most likely distance between these two wires? it shouldn't be within a couple of millimeters, let's say 3-4 millimeters, maximum 5, not more than 5. 2 wires live neutral within a cable for a single operating device, placed side by side. That's one thing. So D has a value should be less than 5 millimeter. 3 millimeter, 2 millimeter is good enough. I wouldn't say a 1 millimeter. 1 millimeter will be too small. So let's say 3 millimeters. And if you consider the current value that usually a typical electrical device uses for our regular purposes, I mean, if you want to even go for the most strongest magnetic field produced, if you think about the strongest of the current, highest of the current that a certain electrical device for our regular life usage could pick up, this has to be something for a very powerful device. For example, let's say an AC or an electrical heater or an electrical iron. If you even consider that one of these devices have about, let's say, 1 kilowatt power, which is not very common for all the equipments that we use. For example, light, fan, TV, refrigerator, they don't use 1 kilowatt power. Few equipments is 1 kilowatt power, but I'm choosing the highest power equipment that's most commonly available for our household purposes to get us a much bigger value. So if you take 1000 watt and divide it by the supply voltage that we have in our household purposes, about 220 to 240 volts. So if I divide 1000 divided by 220, I get about 4.5 ampere of current. So you could get 4.5 ampere current, not very typical, but that might as well be the maximum current for regular normal circumstances. So I can be considered to be somewhere around 4.5 ampere or 5 ampere, you can write, and D can be considered as about, let's say, 3 millimeter. If you place both of these values over here in SI units and eventually calculate the value of B, even so the value of B would come to be extremely small, because the multiplier in front of this fraction I by D is 2.0 10 to the minus 7, which is a very small number. So the product of all of these three values would give you a magnetic field that would be extremely small. And now the force which is responsible to vibrate the wires, if it does any vibration, is given by F equals to BIL sine theta. If B itself is extremely small, then the force would also be very small. That force would be so small that it would not have enough effect onto the wire to overcome its inertia to show us any visible effect. So the if you so the magnetic field would be produced, but the typical values that we can get for I and D, that this 2.0 10 to the minus 7 value that you're saying, this is basically an outcome of the permeability of free space. So this is actually mu naught by 4 pi. This is not introduced in the syllabus, so they just directly gave you this constant. But because this multiplier number, this coefficient number is actually so small, the altogether the value of the magnetic field that is induced by one of the wire onto the other one, that would be extremely small, ultimately resulting in the force to be too small, which would not be good enough to overcome the inertia of the individual wires. Hence, no vibration is seen. That's the physical answer. To score 4 marks out of this question, you have to do reasonable estimates of the values of I and D. This scores you 2 marks. Then you can show a sample calculation of using the values for the value of B, or you can choose not to show that doesn't have any mark, but then mentioning the formula that force is given by formula B equals to F equals to BIL, is mentioning that force formula should score you 1 mark, and then mentioning that this force would be too small because of the 2 × 10⁻⁷ coefficient, and as a result that force would not be able to overcome the inertia of the wires, hence no vibration would be seen. So that's how the 4 marks are usually distributed. We can have a look at the
Sir.
mark scheme to give you a better idea. Just send to it, Koro. Let me finish, then I'll take questions, don't worry. Number 4C, if we have a look at number 4C, such and reasonable values for I and D. Okay, I was wrong, it gives you 1 mark. Mention of expression F equals to BIL scores you 1 mark. Force between the wires is small, so that has to be substantiated by mentioning that the coefficient being too small makes the force to be too small compared to the weight of the wire. In this case, they have used the term weight. We use the term inertia. Either way, you should get the mark. If you have a look at the examination report, you can see that it's a pretty elaborate examination report. A number of candidates did make reasonable estimates and then wanted to show that the force between the wires would be such much less than the weight of one of the wires. However, most candidates scored very few marks. Most did not allow the instruction to make reasonable estimates, and consequently they could not expect to be awarded much credit. Common discussions were that either the wires would vibrate too quickly for the vibrations to be seen, or that the force would always be attractive so that the wires could not vibrate. Force would not be, doesn't have to be always attractive. The conditions can have a change. There can be a bit of phase difference between the forces, and so you can have attraction and repulsion both. So Raya actually asked me the 2 questions. In my opinion, the distance between the 2 cables, since you're still asking me, so let me just show you.
স্যার ওই পার্টটা কথা আসলে একটু মনে হয় কেটে গেছিল, ওই যে 1 কিলোওয়াট পাওয়ারের পরে যেটা বললেন।
Let's say this is one of the typical electrical cables, power line. So let's say this is one of the typical electrical cables. So here you have three wires, live, neutral, and ground. But if you only consider live and neutral wire, what is the most likely distance between two of these metal leads through their insulation? What is the most likely distance between them? That is the value of your D, for how close the two metal wires are supposed to be for a reasonable normal circumstances. And what is the maximum current that you could possibly have? I calculated for a 1000 watt device for a 220 volt supply about 4.5 ampere. So these are the two values, about 2-3 millimeters for D, and about, let's say, 4.5 or 5 ampere current for the current. All right, so that's that. And then the other problem that we have over here is 6b2. বুঝা গেছে কি কোশ্চেন আনসার এখন সবার ক্লিয়ারলি?
স্যার কারেন্ট হচ্ছে 250 অ্যাম্পিয়ার বা ওরকম বললেন।
250 কোথা থেকে পাচ্ছ?
স্যার কারেন্টের ভ্যালুটা কি বলছেন?
কারেন্টের ভ্যালুটা আমি পাওয়ার ডিভাইড বাই ভোল্টেজ দিয়ে বের করছি। P equals to VI এর যে ফর্মুলা আছে, I assumed the powerful equipment for household purpose is about 1 kilowatt. That's pretty high. And I consider the supply voltage 220 volt. I did the division and found the current value.
আচ্ছা ঠিক আছে।
ঠিক আছে, ফাইন, বুঝা গেছে এটা?
জি স্যার।
Beautiful. Question number 6b2. We have 6 over here, B's over here, 2. Acha. So small rectangular coil ABCD consisting of 140 turns of wire, side ABCD of the coil length of 4.5 to 20 centimeters respectively, as shown in figure 6.1. The coil is held within the post of the larger magnet so that the coil can rotate about an axis to the center. The magnet produces
স্যার এটা লাগবে
electromagnetic
না, এটা
flux.
লাগবে না, এটা লাগবে না।
What's it?
একটা বুঝছি আমি পরে।
আচ্ছা,
হ্যাঁ হ্যাঁ হ্যাঁ, এখানে ভুল করছিলাম আমি, লাগবে।
7C. এটা আমরা লাস্ট ক্লাসেও আলাপ করলাম যে আরএমএস ভ্যালুকে যদি আমরা লাস্ট ক্লাস আরেক ক্লাসে মনে হয়, আচ্ছা আলাপ করতেছি আমি, ডোন্ট ওয়ারি।
স্যার ভিডিওগুলো আপলোড করেন না এখনো?
হ্যাঁ, এটা আমার ভুল হয়েছে। আচ্ছা, আমি আজকে ক্লাসের পর সবগুলো ভিডিও আপলোড করে দিব, ডোন্ট ওয়ারি। I will do that. I'll remember to do that. এখানে যে সিচুয়েশনটা হচ্ছে যে whenever we have this current balance, we are sending this is you know how the current balance works. We are sending a current of 4.6 ampere. 2.6 ampere. 2.6 ampere of current produces a reading variation of 2.3 gram. A DC current of 2.6 ampere produces a balance variation of 2.3 gram. The question asking us over here, the direct current is now replaced by a very low frequency sinusoidal current of RMS value 2.6 ampere. So now we are changing the supply and bringing up an AC source that's RMS value 2.6 ampere. Calculate the variation in the reading of the top line balance. So the way this question should be understood is this thing. Have a look. 2.6 ampere DC gives you a current variation of 2.3 gram, and that variation is in only one direction. Either you're going to get additional reading or you're going to get decreased reading. That's pretty much it. Whenever you're going to change it with a 2.6 ampere RMS DC, let's say if that AC is like this, the peak of this DC would be 2.6 ampere root 2. That's the first thing that I need you to understand. Because if the RMS value is 2.6 ampere, the peak value would be 2.6 root 2 ampere. If you wonder why am I talking about peak, because the maximum variation of the weight scale would be happening for the maximum current in the circuit. Maximum variation of the weight scale would happen for the maximum current in the circuit. So you have to deal this problem with the maximum current. That's part one. So, and the second thing is that because in this case for an AC supply, the current is in one direction and then in the opposite direction, you're going to have increase of the value and decrease of the value both. So you're going to have bidirectional change. If your original reading over here was, let's say, 100 gram, for an AC supply, the reading is going to increase for half the cycle, reach to a maximum, and then it's going to decrease from 100 gram on the bottom side. So you're going to have a total variation of this much. So you're going to have double the variation because the current is changing direction. So how much would be your total value change? So 2.6 ampere DC gives you 2.3 gram. So if it was 2.6 ampere, root 2 ampere DC, I mean, I'm not using the, I shouldn't use the right term DC over here, but if this current was just root 2 times bigger, the variation of the reading should be 2.3 into root 2 gram. This would be possible if the current was only in one direction, but because it's an AC, current is traveling in both direction, you have to multiply this by 2 so that you can cover for the addition and also for the decrease. So that's the whole answer for your whole calculation. I'll take question.
বুঝতে পারছি।
All right. So these are the questions from Shubhro. Then Mugdha gave me a problem in personal message. I'm gonna turn up this question. This is October number 1543, question number 6A. When 15. $43. Question number 6A. There you are. এটা না?
Yes, sir.
Acha, let's have a look at this question. Such an explanation for each of the following observation. Two wires are laid side by side and carry equal currents I in opposite directions as shown in figure 6.1. The total magnetic flux density due to the current in the wires is negligible. Okay. This is the same question that we just discussed right now. That for a typical working scenario, the distance between the wires has to be, let's say, a couple of millimeters, 2-3 millimeters, and the current value that we could possibly achieve within these wires are very small. Now they have not given us the permeability equation, that 2.0 into the 1.7 values, but to be able to express work with this equation, you have to bring up that constant, that concept, that the air between the two between the two wires. I mean, how would I write these answers? The way I would write this answer can be like this. Magnetic field produced by a single line of wire that has to be transmitted through air would become really weak, even over very small distances. So the force produced, or I can write that the amount of cutting that the magnetic field, the amount of the total magnetic flux density due to the current in the wires is negligible. Acha, nah, never mind. I wouldn't have to go through that. Acha, sorry, my bad. I was going in the wrong direction. I was trying to think about. Let me tell you why I was wrong. I was thinking in my head that this question was asking us that why these two wires are not seen to vibrate, or why the force is negligible. That's what I was thinking about. But the question is not about the force. The question is about why the flux density due to the current in the wires is negligible. Have a look over here. They have used the term plural over here. The total magnetic flux density due to the current in the wires is negligible. Here's the deal you have to understand. These two wires are placed side by side and they are carrying equal current. So this wire will be producing one directional magnetic field around it, which would be almost perfectly counteracted by the magnetic field produced by this one, because this will be producing the opposite directional magnetic field. Because they are placed side by side and they are quite close to each other, they will almost completely cancel out each other's magnetic field. So because you have two wires placed side by side, uh, they will be put, and they're carrying current in opposite direction, so they will practically cancel out their magnetic field for the around part. But for the in between part, the field would be pretty strong, because if I try, if for those, if you remember the shape of the magnetic field lines that we get from parallel wires carrying current, let me just show this to you with a small drawing. Let's say this is a dot wire and this is a cross wire. Dot wire will produce an anti-clockwise magnetic field like that. Wrong drawing. Dot wire will produce an anti-clockwise magnetic field like that. So I'm drawing one for the inside space and one for the outside space. And then the cross wire will produce clockwise magnetic field. Let me draw that with red. So it will produce clockwise magnetic field. So let's say it's going to produce one magnetic field for the inside space and one for the outside space. So what you should be seeing, that for the in between space they are producing similar direction magnetic field, but for the outside, here the red is going downwards, the blue is going upwards, and over here the blue is going downwards, the red is going upwards. So for all of the outer space over here, for all the outer space over here, for the most space over here and over here as well, the magnetic fields will be pretty much counteracted by the opposing magnetic fields produced by each other. However, for the in between space exclusively, the magnetic fields would become stronger. So the question that is asked over here is that, here, the question is asked over here, the total magnetic flux density due to the current in the wires is negligible, because whenever you have the total magnetic flux density, uh, if you try to measure this, it's unlikely that you will be measuring it at the center. At the center, the magnetic flux density could be significant, but that's also quite small because of the low permeability of the free space. But irrespective of that, for all the spaces around the around this wire pair, the magnetic field lines will be pretty much counteracted. That's uh, my answer. If I was answering this thing, I would be answering in that term, that the magnetic fields would be counteracted by each other. But I'm gonna have a look at the mark scheme and see what points they have for us. 6. Magnetic fields are equal in magnitude and strength of flux density. Magnetic fields are in opposite direction. Fields superpose, add, or cancel to give zero negligible horizontal field. Works out for me. I think that's the correct response. If you look at the examiner's report,
Sir.
just a second. Question is checked. This question needs to be answered in terms of magnetic flux density. Many candidates use flux, force, or current instead. Candidates stating that the fields were equal needed to say that they were equal in magnitude. So only mention the fields would be equal would not be good enough. You have to say the fields are at any location, the field density, the flux density or the field density would be equal with each other and opposite because of the opposite direction of current. So you have to use the term magnitude. Only saying equal would not score you the mark. That's the additional wording based information that we have over here. Hey, I'll take questions. Abias bolo.
Sorry, they didn't mention the flux density between the wires.
Yeah, because what they are assuming that whenever we will measure the magnetic flux density around this thing, I mean, it's pretty unlikely that we'll actually insert a Hall probe between these two wires. If we measure the magnetic flux density around the wire pair anywhere, we'll pretty much get a very weak field or negligible field. So that's what I believe they mentioned, that have we read the question. Two wires are side by side and carry equal currents I in opposite direction as shown in the figure 6.1. The total magnetic flux density due to the current in the wires is negligible. So total magnetic flux density would mean that what is the total sum of the two magnetic field lines. This could have significant value for the space in between. That is a very small and very unique space compared to the whole around space of the wire pair. So they disregarded that part completely, went on for the more generalized explanation.
Okay, sir.
Mukto bucho? Yeah, you raised your hand.
স্যার মানে আমি কনফিউজ হয়েছি কনভেনশনাল ম্যাগনেটিক ফিল্ড ডায়াগ্রামটা নিয়ে অ্যাজ ইন একটা রেজাল্টেন্ট ফিল্ড থাকে তো ফর টু অপোজিট কারেন্ট ক্যারিং কন্ডাক্টরস
Exactly, that resultant field would be strong and be observable for only for the in between space. দেখাচ্ছি আমি তোমাকে, আমি ভালো ফিগার এখান থেকে বের করি। তোমরা 10 দেখছো কেউ?
ইয়েস স্যার
মাথা খারাপ হয়েছে?
স্যার অনেক খারাপ ভাবে।
আমি একবার দেখছি and then I just went on Google that why this ডিরেক্টর নাম ভুলে গেলাম। এই লোকের নাম যেন কি?
ক্রিস্টোফার নোলান স্যার।
Christopher Nolan, exactly. Why Christopher Nolan makes such reverse movies? I just directly Googled that, and I had a lot of responses that not only me, a lot of
স্যার
other
মুভিটার নাম কি?
Tenet. This is the most recent Christopher Nolan movie. It's weird. I mean, it's really bad. I wouldn't say bad. I mean, তোমরা যারা ইনসেপশন দেখছো একবার দেখে বুঝছো, আই ডোন্ট নো দ্য লেভেল অফ ইউর ব্রেন, যারা অ্যাটলিস্ট কয়েকবার দেখার পরেও বুঝছো জিনিসটা কি হইতেছে, আই টোটালি রেসপেক্ট ইউর রেসপেক্টিভ বিকজ I think I understood the whole concept of Inception after seeing it for the 6th time or 5th time, I think. Then for the 6th time, then I saw it one more time just for the fun of it. But it took me a long time to actually understand what is happening over there, for at least to my level that I understood. I'm not demanding that I understood it whole. Tenet is just, like, say, multiple orders of magnitude difficult to make sense. Never mind. আমি কি খুঁজতেছিলাম এখানে? To parallel long ways carrying current images. So this is the image that I'm talking about. If you have a look over here, that whenever we combine the two fields, so for the in-between space, the field can be pretty strong and significant. But for all the other spaces, the field would be really weak because you can see the field lines are actually becoming really spread apart. Because for opposite directional magnetic field. So exclusively for this much space, for let's say about 1 centimeter by 1 centimeter, let's say 2 millimeter by 2 millimeter space of rectangular space within the two wires, you might have a measurable significant magnetic field strength or magnetic flux density. But for everywhere else, that flux density will be really, really weak, almost negligible. So that's what Abias also asked, that why should you say it is almost negligible? Because they considered that quotient was considered for the space around the wire pair, not for the space in between.
Sir, cancellation effect কোত্থেকে আসতেছে? As in, how do they cancel each other out?
Because they produce opposite directional magnetic field. Let me show you. Do we have the kind of field?
Sir,
Yes.
is the field arrangement uniform or symmetrical when the current in the two wires are different?
You can see in this figure, I mean, this is a good, well-done figure. Here they have shown the individual figures as well. So let me just open this image in a new tab. So what you can see over here, that the crosswire is producing clockwise current over here, dot wire is producing anti-clockwise current over here. For the in-between space, the directions of the field lines are pretty much uniform. What you have to understand, what I need you to understand, that these field lines produced by the crosswire are not going to be finished over here. They will be extending over on the right side as well. And these dot wire circles, they will be extended over on the left side as well. So what is going to happen on this side? The field lines coming from the crosswire will be working downwards, but the field lines working from the dot wires will be going upwards. So you'll be having two opposite directional magnetic field working in the same space. Pretty much like the superposition of waves, they are going to cancel each other's effect.
Sir, for an extended view, they will cancel each other out, but for the center, they are very strong.
Precisely. This question was
Okay, sir, got it, sir.
for the around space.
Yes, sir. Thank you, sir.
No problem. Then we have
ওরা না ফোর্সের কথা বলছিল, যে কেন ফোর্স নেগলিজিবল?
They asked precisely about the flux density.
আচ্ছা, ফ্লাক্স ডেনসিটি বলছিল।
আচ্ছা,
মানে ওরা ওভারঅল কনসিডার করে বলছে এখানে।
Yes. Requiem for a Dream is a very, very sad movie. I cried the second time I saw it. Tenet didn't even crack 80% of for any and all scores and etc. Well, here is the deal. if you make a movie that is so I mean that's just my explanation. If you make a movie that is more complicated than it's entertaining, it's not gonna be accepted by mass people. Then it is gonna get traction over time as it slowly produces its own fan base and people start to have more discussion about it, which is not gonna happen in a pretty long time because we are all pretty much messed up for the COVID and everything. So we have other stuff to talk about. So other than Tenet, so it's not gonna take that much traction. But the primary reaction, if you think for the Tenet, I mean, if you see the movie in a hall experience, I mean, it's not a very enjoyable movie. You have to see it over and over uh, if you want to make sense with it. And I don't know after how many watching someone can actually make sense with it. The concept they have used are very paranormal, so it's not there is no assurance that whether it's going to be possible or not. That's the whole point of a science fiction movie, obviously. But it's weird, really weird. Yeah, exactly my point. Tenet might actually achieve a cult later on, its own personal fan base. So yeah, we're gonna pick up next question. I think Mugdhor pore আর কেউ কোনো question দেয় নাই. So do you guys don't have any other question to ask?
স্যার আমি দিছিলাম তো।
আচ্ছা তুমি বলছিলা হচ্ছে কোনটা যেন ডিরেক্ট সেন্সিং না হ্যাঁ ডিরেক্ট সেন্সিং ওয়ার্কশিট প্রবলেম আছে. Okay, I'll pull that up. Putting up the direct sensing worksheet right now. Fine had some problems.
স্যার ওটার কি একটা জিনিস মানে আল্ট্রাসাউন্ড থেকে জিজ্ঞেস করতে চাই, ওটা হচ্ছে মানে বেশি টাইম লাগবে না। মানে একটা কোশ্চেনে ছিল যে আল্ট্রাসাউন্ড হচ্ছে হাই ফ্রিকোয়েন্সি দিলে ইয়েটা কি মানে অ্যাডভান্টেজটা কি ইনস্টেড অফ লো ফ্রিকোয়েন্সি। আর মার্কস স্কিমে লেখা ছিল যে হাই ফ্রিকোয়েন্সি মিনস শর্টার ওয়েভলেন্থ, সো স্মলার স্ট্রাকচারস আর রিজলভড। এই পার্টটা
Yes.
বুঝিনি।
এটার আইডিয়াটা হচ্ছে to be able to see stuffs clearly, you primarily need more energetic waves to have better penetration, and so that the reflected waves can have enough energy to be detected. এটা তো বুঝো. If you
হ্যাঁ
send
হ্যাঁ
really less energetic waves, then they might actually get absorbed, attenuated within the medium, and after reflection, they might become so weak that they cannot be detected properly. So you want to have a high amount of intensity of your sent wave. Now, what are the two ways that we can actually achieve high intensity? Intensity is proportional to amplitude squared, intensity is proportional to frequency squared. If you want to use low frequency wave, then your only choice is to make a really large amplitude for a high intensity. But if you want to make high frequency wave, you can make small amplitude waves with a high frequency and still have enough energy on the wave. The way it helps that, let's say you are trying to visualize an object, or you are trying to take a scan of an object that has a size of this much. If you use large size waves, for example, let's say if I take this much, if you use large size waves and send this wave into this object, we're going to have partial reflection. এই ওয়েভের এইটুকু রিফ্লেক্ট হবে যখন এটা এসে হিট করবে, তারপর এখান থেকে এইটুকু রিফ্লেক্ট হবে, এখান থেকে এইটুকু রিফ্লেক্ট হবে, এখান থেকে এইটুকু রিফ্লেক্ট হবে. So you're going to have fractured reflection. So on the reflection side, you're going to have reflections like these, not full wave reflections, because the object is smaller than that twice a of your object of your wave. You can send a powerful wave, but you are not going to get the full reflection of the wave, so your produced image would be not seen as it is required to be seen. Whereas if you send a low frequency wave of the same intensity, or if you send a high frequency wave of the same intensity where your amplitude can be pretty small, you can have the full wave reflected off this boundary. That enables you to see the object more clearly.
ওকে স্যার বুঝছি।
Beautiful. I mean, this is a question that relevance that to have a powerful enough wave, we need to send high frequency or high amplitude waves. Now, if you choose high frequency, you can keep the amplitude small, which helps us, or which enables full reflection of the wave. That enables us to produce a much better reflection image. That's the simple point answer. Okay,
Yes, স্যার।
beautiful. But distance problem bolo.
স্যার 13 এর C2।
Question number 13. An amplifier incorporating an operational amplifier has three inputs. Okay.
স্যার এগুলা সব
Parts.
পারছি, মানে C এর 2টা লাগবে শুধু।
দেখতেছি আচ্ছা such use for this circuit আচ্ছা this circuit is basically a digital to binary conversion digital binary conversion sorry binary to digital conversion because you can see over here that whenever you have 001 you have output 1 you have 010 you'll get 2 100 you'll get 4 and then 101 will get 5 so you're gonna get pretty much all I mean if you convert these 3-digit binary values in this sequence ABC you'll get all the decimal values over here so this is a simple table that tells you inherently that we are converting binaries into decimals
স্যার এখানে লেখা আছে ডিজিটাল টু অ্যানালগ কনভার্টার।
that's basically binary to decimal
ওকে স্যার। আর স্যার নাম্বার 19 19B B1 and 2
19B that also says why comparing values from figure 9.1 when the tank is nearly full the voltmeter readings give the impression that the fuel consumption is low when the voltmeter first indicates that the tank is nearly empty there is more fuel remaining than is expected B2
স্যার both B1 and 2
Mashrafi well done আচ্ছা B2 টা দেখতেছি when the voltmeter first indicates that the tank is nearly empty there is more fuel remaining than is expected আচ্ছা এইটা কিভাবে এখান থেকে বোঝা যাচ্ছে let's have we can have a look over here this is the tank so this is the voltmeter reading reaches 0 okay you can see that the voltmeter reading is actually becoming nearly 0 at around this point this is where we are having to touch so pretty much when the voltmeter reading gives us a 0 reading we still have about 8 liters of oil left within the tank so the question is searched why comparing values from figure 9.1 when the voltmeter first indicates the tank is nearly empty you see they haven't used the word empty nearly empty there is more fuel remaining than is expected because what we have seen that for this longer duration of the voltage change for this longer duration of the voltage change the volume of the oil and the voltage drop was linear so that's the mindset that the observer would have in their head so whenever they would expect a linear decrease of the voltmeter reading as the volume of the liter goes down but eventually because this over this part the gradient is decreasing which means for the last 20 liter I mean the shown voltage would show you that we have only half volt so maybe representing that the very small amount of liquid oil is remaining but this would require a much longer emptying so because the gradient of the graph is much smaller because the gradient of the graph is much smaller so this will make the voltmeter reading to drop really slowly when close to 0 when the voltmeter would drop very slowly when close to 0 as a result it would imply that there would be more fuel than expected because the observer would expect that the fuel to become 0 pretty soon but it would take a longer time for the fuel to become 0 because that's what we are seeing over here that for the last 20 liters the drop of the voltage is only 0.5 volt 0.6 volt each I'm not being able to make the wording perfectly marks কত এখানে 2 mark না I would have to go for the wording but did you get my point it's about the gradient of the graph losing
yes sir
আমি মার্কস স্কিমে ওয়ার্ডিংটা একটু দেখি তাহলে আর একটু বেটার বুঝাতে পারবো জাস্ট আ সেকেন্ড এটা হচ্ছে কত নাম্বার কত 19 এর বি here we have voltmeter reading nearly 0 when fuel is left voltmeter reading nearly 0 when fuel is still left so that's the first thing that I told you that at around 8 liters voltmeter read is only about 0.1 volt when 10 liters full of fuel left in tank voltmeter read 0 when about 4 liters of fuel left in tank scores 2 marks Oh, if you write the first information, you directly get for 2 marks out of it. Oh, beautiful. Examination reporter will say many candidates did comment that many candidates did comment that there would be fuel in the tank when the volumetric reading is near to zero. Again, comments based on numerical evidence from the graph are rarely seen. So also the primary thing is that we have to mention values. We have to mention numerical values from the graph to substantiate our answer.
স্যার বি টুটা বুঝছি, বি এর ওয়ানটা কিভাবে লিখবো?
B এর 1 বলছে দেখতেছি, suggest why comparing from values from figure number 1 when the tank is nearly full the volumetric reading gives the impression that the fuel consumption is low. Oh, this is because nearly full. So let's consider for, let's say 80. ঠিক আছে? You can see that from 80 liters through about এটা কত? Every horizontal division over here is 4 liters na? No, 2 liters. 2 liters. So for the from 80 liters to 76 liters, the volumeter reading drops by 0, or the volumeter reading does not drop. So it shows no consumption of fuel, even though the fuel is being consumed. So that's one thing. And then as it slowly start to consume more, then the graph becomes steeper, which means for this part the consumption is shown to be very small. Consumption is increasing. Over here you have a steady consumption rate. So if we have a look at the mark scheme, I'm having difficulty making the words. Only 0.1 volt change reading for the first for the 10 liter consumption or similar numbers, and above 6 liter gradient is small compared to the gradient of at about 40 liters. So above 60 liters the gradient is small compared to values around 40. Asha says they have mentioned about gradient, or they have also talked about the voltage as well, that 0.1 লিটার হচ্ছে এখানে। সো 80 থেকে 70 লিটার ফর দ্য ফার্স্ট 10 লিটার ড্রপের জন্য তোমার ভোল্টেজ ড্রপ হচ্ছে শুধুমাত্র half of a small division on the y axis. So you are having only 0.1 volt drop for the first 10 liter, but which is really less compared to what is going to happen for the more emptying, for less volume of oil remaining.
স্যার বুঝছি।
Beautiful.
এইটুকু কি আর নেই এখান থেকে?
আচ্ছা, Abiyaz, you raise your hand. Yes, go ahead.
Sir, calling back to the 13C problem, problem number 13. If
Sure.
if the output of the voltage were like opposite, like it from larger numbers like 4, 5, it gave outputs like 1 and 0. Would you call that an ADC circuit?
Come again. If the output numbers, so if the voltage output was what?
It was like these, like 1, 2, 3, or 1, 4, 5, and it gave you an output of 0 and 1 only. Would you call that an ADC circuit?
An ADC circuit an ADC circuit have to have the capability to convert a certain given voltage into bits produced, which would ultimately mean that equivalent decimal number in binary. Now, if we had a certain circuit which could convert, let's say 5 volt into 101 by 3 different output side, you have to have 3 different outputs. So your first bit MSB, then your middle bit, then your FSB, so LSB. So if you have those bit production from a single input voltage and they were relevant in terms of the binary digital conversion, then you could, yes. But what I want to tell that, because this is working with an op-amp, this whole circuit simply cannot work reverse. I mean, you cannot expect to give 9 volt over here and expect certain outputs over here. This is a one-way circuit. So that circuit would have different designs. Do you understand my point?
Yes, sir. So we wouldn't get a question like that.
You might if they come up with a question like that, but that wouldn't have you wouldn't have to know the necessary complexity or the working principle for that to work about. You just have to beat around the bush and say that how this circuit could be useful, or what kind of input gives what kind of output, and for how can that be manipulated for our benefit. That this is the question that you would be asked about, not for the internal working or the operation of the circuit. No. Do you understand me using the term beating around the bush? Do you understand that part?
Yes, sir. We don't really need to go deep.
Yeah, for your
Yes.
syllabus, you don't need to go deep into the circuits.
Surface level answer.
Precisely. So do we have any more problem from anyone else? Samia, do you have any problems? You are coming up with some really good problems in the last couple of classes, so I really appreciate that effort. Do you have anything for us? Or other people over here, for example, Rayaro Dishi Sultan, Rami Safariha, Rafid Abrar, Rafid Nabi, Rabia, Nusaiba, Mursalin, Muntakim. Muthu gave us a problem today. Fariza. Fariza, how are you?
Sir,
How are you?
I am somehow alive.
Okay. COVID precisely shows us that how fragile our lifestyle is. How we can be blasted into oblivion morally or spiritually and physically, of course, just by a single strain of virus. If you guys don't have any question, I'll stop the class and start uploading the earlier lectures and today's lecture as well. Anyone? Anything else to ask about for today's class? Good night, everyone.
So, sir, I had a problem.
Bolo.
Sorry, it's a 8 beta from the same worksheet.
This one. I'll go have a look. So we have a strain gauge which is fed by two circuits. The equation is given. Well, then good. In B it says that which one? B.
Sir, B2, I'm stuck.
Asha, sure, I'll help. The question, let's have a look at the circuit. Let's first understand this part. What we can see over here that we have a strain gauge. The strain gauge is connected in parallel in series with the 1 kilo ohm resistor with the ground. And this connection, this in between voltage is fed as V2, which is our V plus, the non-inverting input, and V1 is other voltage, which is fed into the inverting input. The equation is already given. V out is given by V out equals to RF by R into V2 minus V1. State the name of the gain ratio. This is the amplification or gain. This is the name of this ratio is gain. The strain gauge has a resistance of 125 ohm when not under strain. Precisely. Calculate the magnitude of V1 such that when the strain gauge is not strained, the output V out is 0. So if it is not strained, if we want the output to be 0, then both of these values have to be equal. That's the only way you can make this 0, because this will never become 0 because these two numbers have physical values. So if these two numbers are precisely equal, only then you can get the output 0. Now the question tells us that when the strain gauge is not strained, it has a resistance of perfectly 125 ohm. From this potential divider circuit, you can calculate out what would be the voltage output of this point when this was 125 ohm. You can calculate this. 1000 divided by 1000 plus 125 into 4.5. এটা বুঝছো?
স্যার এই পার্টটুক বুঝছি, কিন্তু স্যার আমি কনফিউজ যে V2 যেটা সাপ্লাই করছি তখন আবার এটা isn't that getting added to the voltage which was already there from the potential divider circuit?
Oh, here's the deal. If the output of the output of the op amp is precisely 0, then RF would not actually add any fraction. So if the strain gauge is it has a output voltage, I mean if the strain gauge connection has an output voltage which is V plus or V2, which is exactly equal to V minus, then the output will be 0. So the feedback fraction would also be 0. So you would not have any feedback. So that state can be maintained indefinitely.
And স্যার আরেকটা জিনিস ছিল যে like why do we consider this point to be a virtual মানে আমরা যে আপনি বলেছিলেন যে আমরা যে we consider the V plus to be V minus for an inverting amplifier. স্যার ওই পার্টটা একটু বলবেন যে আরেকবার?
Sure. So you're asking about this thing. The idea is that for the non-inverting, as for the inverting amplifier circuit, the non-inverting input V plus is always fed from ground. So non-inverting input is always 0. For the output of the op amp not to be saturated, the inverting input and the non-inverting input has to be really close, like super close, so that the input value voltage is very small, so that whenever you multiply it by the gain, you can avoid saturation. That's a theoretical aspect. Because we want these two voltages to be really close, but not exactly same, because exactly same would give us precisely 0. We don't want that to happen. But to avoid saturation, these two voltages have to be really close to each other. So P has to be really close to 0. So the way we say that V plus equals to 0, whereas in this case V minus has to be approximately equals to 0. That's why we are naming this P point as virtual earth. It's not exactly 0, but it has to be really close to 0 to avoid saturation. বুঝাচ্ছে?
Yes sir, বুঝছি এখন.
Beautiful. Anything else?
So, sir,
বলো।
in that question, Rafi mentioned negative feedback wouldn't do anything.
In this one? Oops.
No,
sorry.
sir.
In the question?
Yes, sir. In the question.
Here you would have this negative feedback ultimately added up with the V1, and eventually this will help us for the circuit to working. But if you ask me, I precisely do not know how this circuit is going to work, because I haven't studied about it, because we have two different feedback resistances over here. I really didn't study about this, and you don't have to either, because this level of circuits are not included in your syllabus. I mean, what if we add multiple resistors in different places, and what's going to happen? That's the reason why they already gave us the working equation for this circuit to work about, and then we have to go about answer questions based upon this equation. How this equation came into existence is, we don't have to bother about that. But well, obviously we can see that the feedback resistance is over here, but the question that you're asking, that if the output is 0, then the feedback fraction will also be 0. Because how does the feedback fraction essentially gets added to our equation? If you have a look over here for the feedback fraction basic idea, have a look over here, that V out is given by A naught, which is the gain into amplifier to the input, which is given by V in plus a beta, which is the fraction, feedback fraction, comes to the resistor, into the V out. So if your V out is precisely 0, then your input is only input. So if your output is maintained at 0 voltage, then your feedback fraction will also be 0. That way your circuit can maintain that equilibrium for an indefinite period of time, unless any of the input variables change.
So we just need to find the voltage for which V1 and V2 are equal. That's it.
For this question, we are asked precisely that for when V out has to be 0. So first you have to give a logic that V out can be 0 only if V2 minus V1 equals to 0, which means V2 equals to V1. So we are calculating V1 using the logic that V1 and V2 would be equal. So mathematically we'll be calculating the V2 value, And by logic, we'd state that V2 and V1 has to be equal for the output to be 0. So that is the value of the V1. So you have to write both of these parts. If you have a look at the mark scheme, they have precisely given some mark for mentioning that as well. This is question number 8b. Here we have the 8b question. So it says that AJ, this is the statement for which you score 1 mark. This is the decision making statement. For V out to be 0, V plus A should be equals to V minus, or V1 should be equals to V2. This statement is important because we are practically trying to find out V1, but we are actually calculating V2. So why these values should be equal, you have to mention that out in a specific statement, properly structured statement. Scores you 1 mark.
Okay, sir, I got it.
Beautiful. All right, let's call it a day. I'll upload the questions, I'll upload the lectures, and you can go through the lectures if you need, and then I'll be solving more problems in the next class, inshallah. And you'll be having, for many of you are asking about your mock processes, you'll be having your topical mocks for the entire month of January, and then you'll be having your full syllabus mock through March through February through April, all the 3 months. So mocks are upcoming, so get busy with your studies. I know you have been busy with your studies, and keep safe. Whatever you do, keep safe. Good night.